right. Good to see you again, computer. I mean, I wish I was talking to a person, but here we are. This topic is pretty deep. I mean, it goes on for a long time, and an intro in 15 minutes, good luck, but I'm going to try. There'll be some other videos in addition to this. In our textbook, Chapter 9 is all about stoichiometry, and just on a common sense level, I said it's something like equating amounts of chemicals to each other. If I want to react compound A with element B, then how much of each one should I use to be safe for one thing, but also not to waste much in addition, because chemicals cost money. So anyways, long stories, but let's compare grams of one chemical to grams of another one. If I were going to say get a successful, well-balanced, efficient, non-wasteful, safe reaction. Sometimes I call it the recipe. I'm looking up how much of one substance to use and how much of another substance to use. It calls for a certain amount of each one. So for example, it could be that A plus B goes to C, and maybe a certain number of A, certain number of B, certain number of C, X, Y, and Z. Generally, I don't know if this will help, so I'll just go through this quickly and see if it helps. If I want to know grams, if I had no grams of A and I want to know grams of B, I do 1, 2, 3 conversions. I convert grams of A to moles of A, just like we've done since chapter 1 or 3, a long time ago, I can't remember. Convert grams of A to moles of A with a conversion factor. Then once you have that number, and honestly I don't even bother to get that number, I just go ahead with my next conversion. If I'm trying to get rid of moles of A, those go on the bottom. Moles of A and moles of B go on the top. That's what I'm trying to discover. Well, actually, I'm trying to discover grams of B, but the intermediate step is the middle step. Duh, that's redundant. The intermediate step, the middle step, is comparing moles of one thing to moles of another. And that comes from the balanced equation. X moles of A relate to Y moles of B as referenced from the balanced equation. This is called the mole ratio. B to A to B, so put the moles of A on the bottom, moles of B on the top. If I did that math, that would give me the moles of B. Then lastly, third step, is I take moles of B and change it back to grams of B. 1 mole of B should be obvious from the periodic table about what the molar mass is, so that fills in with a certain number of grams per mole. Same for this, and these numbers come from the balanced equation. Well, as you might guess, there's nothing special about A and B. What about A and C? Same story. Or what about B and C? Same story. What about C and B? Same story. Take your pick. Doesn't matter. It all looks the same. I mean, I see patterns in all of it. You know, in case that doesn't make any sense, and likely it doesn't, let's get some examples going. So here's a balanced equation. 4 ammonia molecules, 5 oxygen molecules, 4 NO molecules, 6 H2O molecules. Except I can't count in individual molecules, so I think about moles. 4 moles of this, 5 moles of this, 4 moles of this, 6 moles of this, and any other mole ratio you can think of that works. 8 and 10 and 8 and 12 would also work. 2 and 2.5 and 2 and 3 would also work. But what if I had 50 grams of ammonia NH3? And I'm curious, how much O2 should I use? How much oxygen molecules, how many grams of oxygen in the form of oxygen molecules will be needed for 50 grams of ammonia? Well, you know what? There's no way to know. I mean, there's a way to know, but you just can't look at it. You need a piece of scrap paper and a calculator in a few minutes. So I take 50 grams of ammonia and change it to moles of ammonia. Nitrogen weighs 14, hydrogen weighs about 1, so that adds up to about 17 grams for a mole of ammonia. But I'm not going to stop there. My grams would cancel. 50 divided by 17 will give me the moles of ammonia. But like I said, don't stop there. Go ahead and do another conversion. This gives you the moles of ammonia in red, but let me take the moles of ammonia on the bottom, change them into moles of oxygen on the top. So and that comes from the 5 to 4 ratio in the balanced equation. 4 of these to 5 of these. 4 of these react with 5 of those perfectly well. So here my moles of NH3 would cancel and create moles of O2. But I'm not going to stop there. I'll do one more step. I'll take moles of O2, put them on the bottom, change it to grams of O2 on the top. You know, once you get the hang of this, they all look the same way. They all grams, a gram to gram comparison of two chemicals in a reaction and some stoichiometry. It looks all very, very similar. The mathematics goes 50 times 5 times 32 in the numerator, divided by 4 and 17 in the denominator. It comes out to about 118 grams of oxygen. So, there's no way to know that this would be 118 before actually doing the calculation, unless you're a chemical savant and just can do that in your head, but I'm not. Or why did I pick on oxygen? Why didn't I pick on nitrogen monoxide? NO. True. So 50 grams of NH3 would produce how much NO? Similar story. Change grams to moles, just like we did before. I'll write this slightly differently. I'll say the grams of ammonia change to moles of ammonia. Then I put the 4 moles of ammonia downstairs. Oh yeah. And this 4 also relates coincidentally to this 4. I mean, 4 of these give 4 of these. So there's a 4-to-4 ratio or 1-to-1 ratio. But I always write it like this to remind myself where this conversion factor comes from. And it's not. It is 1-to-1, but the balanced equation says 4-to-4. So I just go ahead and write the 4-to-4. Notice in the red, I've imagined changing to NO from the NH3. NH3 was in purple, but now all of a sudden I've changed to NO with this conversion factor. And my last conversion factor would be moles of NO to grams of NO. 14 plus 16 is 30? Yeah. And the math is the numerator. 50 times 4 times 30 divided by 17 and 4. So this one changes a little bit. Or why didn't I ask about water? And you can. So 50 grams of NH3 starts out exactly the same way. I change grams of NH3 to moles of NH3. It's a 4-to-6 ratio, 4-to-6. So I put 4 moles of NH3 on the bottom, just like I've done before. Except now I'm asking the question about water, so I put 6 moles of water on the top. So I should show my cancellations. Grams of NH3 cancel, moles of NH3 cancel, moles of water cancel, and finally I've converted it into grams of water. And so it looks like I had a little bit of rounding error, taking all that, summarizing it back into the equation. But really this plus this should equal very close to this plus this. Mass before, mass after, and then again there's no way to know without that stoichiometry what I'm talking about. How about balancing this little crazy thing? So C2H6 plus O2 gives CO2 plus H2O. And I might say, well, 2 carbons over here, put a 2 carbons over here, 6 hydrogens over here, put a 3 times 2 is 6 hydrogens over here. But when I do that, I got a problem because that's 3 oxygens. And 3 oxygens is an odd number of oxygens on the right-hand side. No matter what, it'll never equal this even number of oxygens if I'm trying to balance with a whole number. So I put a frowny face and said, rats, that won't work. But what will work is if I double it. If I double this and double this and double this, then just about everything else works. That's 2 times 2 is 4 carbons, 4 carbons. 6 times 2 is 12 hydrogens, 6 times 2 is 12 hydrogens. And now 6 oxygens plus 4 times 2 is 8 oxygens. 8 plus 4 is 14. So 7 times 2 is 14. So there's my balanced equation. We've been doing that for quite some time now. Hopefully you can jive with that. So I'll just make up a number. And the number I make up, really, I'm just making it up, is 37.5 grams of water. And I could have made up a number for this, or I could have made up a number for this, or I could have made up a number for this. Because really anything is possible, certain quantity, make up your number. But once I've made up even one number, that fixes everything else in the balanced equation, according to the balanced equation. But again, it takes some stoichiometry. So again, change grams of water to moles of water, first step. Second step, compare moles of water to the moles of whatever you want to know. So here I'm imagining I want to know the C2H6 amount. All these are probably gases, so it's really hard to actually weigh the gases, but you could do it. I mean, you could do it directly, but trickery. Anyways, 6 moles of water come from 2 moles of C2H6. 6 moles of water, 2 moles. And so the moles of water cancel. And the last step is to convert moles of C2H6 into grams of C2H6. The cancellations look like this. The math looks like that. And we've seen it before. The pleasure of this video in a PDF is you can go back and look at it until your heart's content and ask me a really good question. Or I can go back with the same amount of water, ask the same question about oxygen. How much oxygen and what mass of oxygen would be created? And the only thing that changes then is the mole ratio, and then I'm changing moles of oxygen to grams of oxygen. And the cancellations, just like before, and the math, not quite like before, because some of the ratios, this had changed and this had changed, but this would be the same. Or Let's make up a different amount. What if I made up 117 grams? I totally made that number up of, let's see, this ethane gas. And I want to burn it. How much carbon dioxide would be associated with that? So I change grams of C2H6 to moles of C2H6. And then I convert moles. I compare the moles of C2H6 to moles of CO2. 2 moles of this to 4 moles of this. And then I compare or convert the moles of CO2 to grams of CO2. I don't always write the CO2 over CO2. Sometimes I leave that off, especially if I'm practiced and I know that I'm trying to change carbon dioxide from moles to grams anyways. Do the math, comes out to 343 grams. Another way to write that is something like this. Say, start off with a certain amount of one chemical, change grams to moles, then take moles of that chemical, compare them to moles of what you're curious about, and then moles of what you're curious about back to grams of what you're curious about, trying to discover. Some students like to write it like that, or it makes sense to them. Here's another one. Another way to say it. I call the balanced equation the recipe, and the recipe calls for a certain fraction or certain ratio of moles. So 2 moles, 7 moles, 4 moles, 6 moles, or double it, or take it times 11, or divide it by 10. Take your pick. Anything works. But what if I'd said something silly? What if I wanted 2.75 moles of O2? 2.75 moles of this. Well, how much of this? Or how much of this? Or how much of this would I use? Well, that's a good question, but it's pretty simple. It's a pretty simple, relatively simple conversion. I would just take 2.75 moles of O2, look at the balanced equation. It says 7 moles of O2 relate to 6 moles of H2O, and that the moles of O2 cancel and convert to moles of water. Or if you really wanted to, you could take the moles of water and convert it to grams of water by multiplying this by 18, like that. So in a way, this is saves a step if they're asking about moles. Here's moles of water. I just totally made this up, 3.83 moles of water. How many moles of this would it take? Well, that seems kind of random, and indeed it is. I made it up. But I can use this ratio of 6 to 2 or 2 to 6 to convert that moles of water to moles of moles of C2H6. Or if I wanted to, go with the next conversion, take the moles of C2H6, times it by the molar mass of C2H6 to find the grams of ethane. Interesting. Or take moles of oxygen. Take a random number and look at the mole ratio of 7 to 4. Right? 7 to 4, 4 to 7. Moles of O2 go on the bottom, 4 moles of carbon dioxide go on the top. Another one? My goodness, that's a lot. Okay, so once again, make up a number of moles and look at the 4 and look at the 2, or look at the 4 and the 7, or the 4 and the 6. Because once I fix this, all the mole ratios describe a recipe that I should follow if I want a good mixture, an efficient mixture. 17.9, 4 to 2, 4 to 2 converts to C2H6, or convert that to grams in the last step if you want. All right, that's, I think, all I have to. That's a mouthful. You'll have to practice that, and there's some other twists and turns along the way. But those are the basics of changing grams of one compound, comparing grams of one compound to grams of another compound in a chemical reaction. See you in class, guys. Thanks for working hard.